Good evening, everybody. A very warm, if muggy, welcome to you all, young and old, near and far, beginners and experts, and especially to our guest and speaker this evening, Dr. Susan Cartwright. Susan is Senior Lecturer in Particle Physics and Astrophysics at the Department of Physics and Astronomy at the University of Sheffield. She did her first degree at Glasgow University, graduating with a first-class degree in astronomy and natural philosophy. Glasgow taking the view that if it was good enough for Newton, it was good enough for them. Didn't change the title to physics until the 1980s, when the two departments merged and someone decided that the Department of Astronomy and Natural Philosophy was too much of a mouthful. Susan then went on to do a PhD in particle physics, also at Glasgow, and spent 5 years in Hamburg and 2 in California before joining Sheffield in 1989. Since then, she's worked on the Aleph detector at CERN and the Antares Neutrino telescope in the Mediterranean Sea, before becoming a founder member of the T2K neutrino experiment, which started taking data in 2009. The experiment's latest achievement, this is latest in January, which made the front covers of Nature and which Nature chose as one of the standard results of 2020, was to provide evidence that there is a difference in the behavior of neutrinos and antineutrinos, which might help to explain why it is that our university is made of matter and not a 50-50 mix of matter and antimatter. Susan has 2 budgies. We may actually get to hear them chirping in the background during her presentation. She, but not the budgies, speak French and German, and Susan has made an unsuccessful attempt to learn Mandarin when running a joint degree course with Nanjing Tech. The teacher said that her handwriting in Chinese is excellent, but unfortunately her ability to remember what the characters means rather less so. Susan, the floor is yours.
Thank you. So I share my screen. Okay, so I hope you can all see my slides. So this evening, as Nick said, I'm going to talk about supernovae and supernova neutrinos, which is something that I've been working on with a PhD student, and I'm very pleased to say that the student who worked on this won the IOP thesis prize this year for the best particle physics PhD thesis, so I'm very pleased with that. I might also add that it was also one of the best written theses I have ever read, which is mildly embarrassing because the student in question is German. So clearly the German education system teaches German students to write better English than our education system teaches our students to write, but never mind. So get this thing, thank you. So this talk will have 3 parts. First, I'm going to talk about what are supernovae, and then unsurprisingly, what are neutrinos, before finally putting them together to explain the importance of neutrinos to supernovae. So my first topic is what are supernovae? And supernovae are the explosive deaths of stars. So how does that happen? Well, in order to understand that, we have to understand the life cycles of stars. And probably most of you know that if we plot the brightness of stars against their color, we find that there are well-defined structures in that plot, and The most obvious one is a diagonal band from upper left to lower right called the main sequence, because most stars are on it. And main sequence stars are powered by hydrogen fusion in the star's core. So the Sun, for example, which is a main sequence star, is powered by converting 4 hydrogen nuclei into 1 nucleus of helium. The helium nucleus weighs 0.7% less than the total of the 4 hydrogen nuclei, and that 0.7% of the mass is converted into energy using Einstein's E equals mc squared, and this is what powers the Sun. And these fusion reactions go faster if the star's central temperature is higher, and the central temperature of a star is determined by the pressure in the center of the star, which in turn is determined by the gravitational force that the star's mass exerts on itself. So the more massive a star is, the hotter its central region is, and therefore the faster these fusion reactions run, and the more luminous the star is. So on the main sequence, these stars at the top left, the brightest, are the most massive stars, and they also are whiter in color or bluer in color because they have higher surface temperature. So a more massive star than the Sun is typically both bluer in color and much brighter. And the brightness does not go linearly with the mass. A star like Sirius, which is about double the mass of the Sun, is not just double the brightness of the Sun, it's more like 20 times the brightness of the Sun. So what that means is that a more massive star will tend to run out of fuel faster, because although it has more mass, it is using that hydrogen up at a much higher rate. And when a star runs out of hydrogen in the core, the next step is to use hydrogen outside the core, and this makes the star less stable, and this causes it to become a red giant. So the Sun, for example, in about 4 or 5 billion years' time, will evolve off the main sequence and will get brighter, much brighter, although cooler, paradoxically, and much larger. And it will certainly, during that stage, get large enough to engulf Mercury. It may or may not swallow Venus and ourselves, but that will be later in its evolutionary stage. After the red giant stage, stars try fusing heavier elements, initially helium, and a star like the Sun will never get beyond helium fusion. So the Sun is not destined to explode as a supernova. It is not sufficiently massive to go through the procedure that results in that. But a star which is more than 8 times the Sun's mass will get hot enough in the center to fuse heavier elements. It will go from fusing helium to carbon, to fusing carbon to oxygen, and then fusing oxygen to make magnesium, and so on, until eventually the star will form a central core which is made of iron. And as I said, the more massive a star is, the hotter its central temperature, and the faster all these reactions happen. And what this means is that massive stars live for a far shorter time than our Sun. And this is a plot that shows the lifetime in years against the mass in solar masses. So the Sun will live for about 10 billion years. And it's currently 4.6 billion years old, so it's about halfway through its life cycle. But the stars that will explode, the stars greater than about 10 solar masses or so, live for much shorter times. So of order of a few tens of millions of years rather than 10 billion years. So what this means is that even though the lifetime of a star like the Sun is comparable to the age of the universe, these massive stars that explode have short lifetimes, and so they explode when chronologically they are really quite young compared to the Sun. And so if you are looking for supernovae, you tend to find them in regions where new stars are being formed. So ironically, you look for stellar deaths in regions of stellar birth. I said a couple of slides ago that the end point of the evolution of a massive star is when it forms an iron core. Now, iron has atomic number 26, and of course, we find in nature elements with atomic numbers up to 92, and we can manufacture in particle accelerators up to atomic number 118 or so. So why should a star stop at iron? Well, this plot explains why stars stop at iron. I said that a helium nucleus has a mass which is 0.7% smaller than the mass of its constituent parts. And that lost mass is what holds the nucleus together. It's what's called the binding energy. In order to separate a proton or a neutron from a helium nucleus, you have to supply energy to compensate for the potential energy that is holding them together in the nucleus. And the higher that binding energy is, the more energy you would have to supply the nucleus to break it up, or conversely, the more energy that is released when the nucleus is formed in the first place. And you can see on this plot that iron, with an atomic mass of 56, is at the peak of this binding energy curve. So a nuclear power reactor takes heavy isotopes and breaks them apart, so you move up this slope, and that releases some binding energy, and that's why fission of uranium or plutonium can be used to generate power. Conversely, what stars do is they start from hydrogen, which obviously has zero binding energy because it's just a single proton, and they fuse hydrogen nuclei to make heavier elements. And again, that is releasing binding energy, and therefore it's releasing energy into allowing your star to shine. You can also see here why stars spend most of their life on the main sequence. The energy gain in fusing hydrogen to helium is much larger than any other fusion energy gain. The next step is fusing helium to carbon, and that generates only about 10% as much energy as fusing hydrogen to helium. And so the helium fusing stage of a star's life tends to be much shorter than the hydrogen fusing stage, because the star needs to be generating energy to maintain its form against gravity. The whole of the lifetime of a star is a balancing act between pressure and gravity. Gravity would like to make every star into a black hole. Pressure would like to push every star out into a giant gas cloud. And in order to balance these, the star needs to be generating energy in its core. If it is not generating energy, then gravity will win over pressure and the star will collapse to a compact object. So because these later fusion stages generate less energy per unit mass, the life cycle of a star speeds up as it moves from fusing hydrogen to fusing heavier elements. So our sun will live for about 10 billion years fusing hydrogen to helium, but for less than 1 billion years fusing helium to carbon. And that's simply because this is a less efficient process. But once you get to iron, you're at the top of the curve. Nothing you do is going to generate energy by reprocessing iron. If you fuse it to heavier nuclei, you will go down this curve, so it actually costs energy to fuse it to something heavier. If you try to break it up, you will go down that curve, so it also costs energy to break it up. So when a star has produced an iron core, it is in deep trouble. And so once that iron core exceeds a certain critical mass, about 1.5 solar masses, it's unable to support its own mass against gravity, and it will then collapse under gravity. And so great is the gravitational force that it becomes energetically favorable for the protons and the neutrons and the electrons in the core of the star to combine to form neutrons. Now, usually protons and electrons won't do that because the mass of a neutron is greater than the mass of the proton plus the mass of the electron. So in order to form the neutron, you have to add additional energy. So you have to fire the electron at the proton with sufficient kinetic energy to convert to the extra mass. But in this special case of this collapsing stellar core, because the neutrons are much more compact than the protons and the electrons, you can essentially get this extra energy from the gravitational potential energy that you lose by allowing the stellar core to collapse to a smaller size. And we can see this by comparing white dwarfs, which are the end states of stars like the sun, and which are made mostly of a mixture of carbon and oxygen nuclei, with a neutron star, which is the end state of this collapsing iron core. Or a typical white dwarf will weigh somewhere between 60% of the sun's mass and just over a solar mass, and it's about the size of a planet. So a 0.6 solar mass white dwarf would be about the size of Jupiter. A neutron star weighs about 1.4 times the mass of the sun, and it's about 20 kilometers across. So you could fit it inside the M25, no bother. And that tells you how much more closely together you can pack neutrons than you can pack nuclei and electrons. So you form this neutron star, and the surface of a neutron star is unbelievably rigid. I mean, the surface of something like the desk that this laptop is sitting on seems pretty hard, but that is mostly just the probability cloud of the electrons around the atom. So in essence, it's largely empty space. Whereas a neutron star is effectively a single atomic nucleus 20 kilometers across. It's incredibly hard. And so the outer material of the star, which has started to collapse following the collapse of the core, just bounces off the neutron star and produces an outward going shockwave. And notionally, this shockwave should be what powers the supernova explosion. But for decades, when we tried to simulate this in computers, the supernova failed to explode. In fact, what happened was that since there is more material falling in from greater distances, your initial shockwave gets stalled under the pressure of this infalling material, and the whole star just collapses into a black hole. So supernovae in computers signally failed to explode. And this is, of course, rather embarrassing, because we know that at least some massive stars do explode. Most of you will probably remember supernova 1987A in the Large Magellanic Cloud. You know, and we have records, historical records from people like Johannes Kepler and Tycho Brahe of supernovae in the Milky Way. So supernovae unquestionably explode. So it was somewhat embarrassing in the at the end of the 20th century that our models of supernovae didn't explode. And it appears that the key players in this are in fact neutrinos. This collapsing core makes a huge number of neutrinos. You form a neutrino every time a proton and the electron combine to make a neutron, but also this material is so hot that you can form neutrinos by other reactions as well, in similar ways to the ways that they are formed in particle accelerators. And there are so many neutrinos and the material is so dense that even though normally neutrinos are incredibly weakly interacting and tend to go through things, enough of them interact with the material of the collapsing star and they inject enough kinetic energy to restart the shock and cause the star to explode. So one reason for studying supernova neutrinos is that, as far as our models tell us, neutrinos are absolutely necessary to get massive stars to explode in the first place. And I should add that the fact that these massive stars explode is rather important to you and me, because a lot of the heavy element content of the universe is formed in the last stages of a star's of the lives of massive stars in the extremely hot and dense environment around the newly formed neutron star. And if those heavy elements were not disseminated into the interstellar medium by the supernova explosion, but instead were all sucked into a black hole, then it would be much more difficult for life like ours to evolve. As an example, the oxygen that we are currently breathing was all formed in core collapse supernovae. So if these stars did not explode, oxygen would be a rare element in the universe. And this, I put it to you, would not be a good thing. So that was a quick tour of what is a supernova. So the second part of the ingredients of this study is what are neutrinos. And as a particle physicist, the things I work with are the particles of the Standard Model, which are, as far as we can tell, the fundamental building blocks of ordinary matter. I say ordinary matter because one of the problems that we have at the moment is that there's huge amount of astrophysical evidence for dark matter, and none of the particles in this chart is a suitable candidate for dark matter. So this is probably not a complete list, but it's a complete list of everything we actually know about. So in the Standard Model, we have quarks in magenta here, which are bound together by the strong force to produce particles like protons and neutrons. So a proton is 2 up quarks and 1 down quark. A neutron is 1 up quark and 2 down quarks. And heavier and more exotic particles that you make in particle accelerators. And besides the quarks, we have the leptons in green. And the one you are familiar with is the electron. It has 2 more massive siblings, the muon and the tau. And just as the quarks come in pairs with a difference of 1 unit of charge, so the up quarks have charge 2/3 and the down quark have charge -1/3, the same is true of leptons. The electrons have charge -1 and they have a partner, the neutrino, with charge 0. And the 3 neutrinos, there is 1 for each charged lepton, are all very similar to each other and rather different from all the other particles of the standard model. For a start, all the other particles, the purple ones and the first row of green ones, are charged, and that means that they can exchange photons and interact by the electromagnetic force. And this, of course, is the force that holds electrons bound to atomic nuclei, and it's the force that, that basically holds atoms in molecules and is essentially responsible for you being a discrete person and not sort of collapsing into a blob on the floor. Neutrinos are the only constituents of matter that are electrically neutral, so they don't feel the electromagnetic force, and they interact only by the weak force and gravity. And the weak force gets its name for a reason. Neutrinos are remarkably difficult to persuade to interact. So if you were to hold your thumb out in the direction of the sun, approximately 65 billion neutrinos pass through your thumbnail every second as a byproduct of the hydrogen fusion going on in the sun. And it doesn't actually matter if the sun is below the horizon when you do this, because those neutrinos will pass through the Earth without really noticing that it's there. And for this reason, neutrinos have historically been extremely difficult to study. Indeed, it took 25 years from the first suggestion that they might exist, which was due to Wolfgang Pauli, and them actually being detected as byproducts of a nuclear reactor by Fred Reiners and Clyde Cowan. And Pauli was very relieved by this because he had been very concerned that he actually postulated a particle which it would be impossible to detect. And as a good scientist, he was very concerned that any theory he came up with should be testable, and he was worried that the theory of the neutrino was not going to be testable. Fortunately, he had underestimated the persistence of experimenters. So what are the properties of neutrinos? Well, they are best defined by what they don't have. They have extremely small mass. It's certainly less than 1/250,000th of the electron mass. In fact, this slide is a bit out of date. It should now say certainly less than 1/500,000th of the electron mass, and almost certainly less than 1/1,000,000th of the electron mass. And the electron itself is of very small mass. I mean, the electron mass is only about 1/1800th of a proton mass. So neutrinos have neutrino masses are very, very small indeed. And for about 30 years, we just assumed that they were totally massless, and it's only in the at the end of the 20th century that we got good evidence that this mass, although very tiny, is not actually zero. Their electric charge, on the other hand, is definitely zero. So they have very small mass and they have no charge. What they do have is a quantity called lepton number. The standard model does a lot of bookkeeping, and lepton number is essentially the total number of leptons in the universe, so electrons, muons, taus, and the three kinds of neutrinos, minus the total number of antileptons in the universe, so positrons, anti-muons, anti-taus, and anti-neutrinos. And that number, as far as we know, is conserved. So you cannot simply destroy an electron. You can annihilate it with a positron, because then you've destroyed one particle and one antiparticle, and the total number is conserved. And you can convert an electron into an electron neutrino, because then, although you've changed its nature, it still comes into the sun. But you can't just swallow an electron and have it disappear. A thing which has become apparent over the last 20-odd years is that although we talk about three types of neutrinos, one associated with each type of lepton, so there's an electron neutrino, a muon neutrino, and a tau neutrino, and indeed the Nobel Prize for Physics for 1988 was awarded to Lederman, Steinberger, and Schwartz for demonstrating that the muon neutrino was a different thing from the electron neutrino, that if you produced neutrinos in association with muons and they subsequently interacted, they always produced muons again and not electrons. But it turns out that that experiment was not telling the complete truth. If you allow the neutrinos to travel a long distance, then they can change their identities. So a neutrino that was produced as a muon neutrino can later interact as if it were an electron neutrino. And that's what we study at the experiment that I work on, T2K. And that, in fact, won the 2015 Nobel Prize for Takaaki Kajita of Super-Kamiokande and Art MacDonald of the Sudbury Neutrino Observatory, which were the two experiments that demonstrated beyond doubt that this was the case. Super-K looking at neutrinos produced by cosmic rays, and SNO looking at solar neutrinos. And this indeed turned out to be the solution to the infamous solar neutrino problem that for many years experiments detected fewer neutrinos from the sun than we knew the sun must be producing to generate the energy that it does. What the SNO experiment demonstrated was that the neutrinos were indeed produced, but when they reach Earth, only about a third to a half of them, depending on their energy, are still electron neutrinos. The remainder are muon and tau, have converted into muon and tau type neutrinos, which most neutrino experiments can't detect at such low energies. SNO could detect them and could therefore demonstrate that they are indeed there. But anyway, that is by the by. We are interested in neutrinos from supernovae. And obviously, to study neutrinos from supernovae, you would have to detect them. And if you think about it, it is obvious that in order to detect something, that something has to interact in some way with your detector. Interactions in particle physics are described by the exchange of a force particle, and the force particles of the weak interaction are the W and Z bosons, which were discovered at CERN in the early 1980s. And the W boson is charged, and so it causes an exchange of charge between the participants in the interaction. So in this one, a muon neutrino and a neutron exchange a W, and the muon neutrino is converted into a muon with negative charge, and the neutron is converted into a proton with positive charge. So the total charge is still 0, but a unit of charge has been exchanged between the two legs of the diagram. And in this case, your experiment can detect the produced muon. We're very good at detecting and measuring charged leptons. They are frequently important products of particle interactions, and they are easy to identify in detectors. Okay, sometimes the neutrino will interact by exchanging a Z with the target, and because the Z is neutral, the neutrino transfers energy and momentum, but it does not transfer charge, so it remains a neutrino. And this obviously is harder to detect because you don't get a nice clear charged lepton, but you can sometimes detect the effect on the struck particle. So your struck particle may recoil measurably in your detector. It may break up. In this case, the incoming particle is excited to a more massive particle called the delta, which subsequently decays, producing a pion, and that pion, which is an unstable particle, can be detected in your detector. What SNO did to measure low energy muon neutrinos and tau neutrinos was they were using heavy water, which contains deuterium instead of ordinary hydrogen. And deuterium is a rather weakly bound nucleus. And sometimes this exchange of a Z would break up the deuterium nucleus into its constituent proton and neutron. And the neutron would subsequently be captured by another nucleus, and that capture results in the emission of gamma rays, which SNO could detect. So this was what enabled SNO to demonstrate that there were solar neutrinos interacting in their detector that were not interacting as electron neutrinos, that were interacting as mu or tau neutrinos. It's easy to get seduced by looking at these diagrams into thinking that that life is simple. Your neutrino enters your detector, interacts, and you detect it. And it's important to remember that this is not true. What almost always happens when a neutrino enters your detector is absolutely nothing. Only a very tiny fraction of neutrinos interact at all, and therefore, if you do neutrino physics, the only way you can do this effectively is to combine a very large detector to give the neutrino the maximum possible chance of interacting, and a very intense source of neutrinos. So things like nuclear reactors, the sun, remember 65 billion neutrinos per square centimeter per second, and intense neutrino beams produced using particle accelerators. It is not that you will detect any specific neutrino. If you wanted to detect a specific neutrino, your detector would have to consist of a couple of light years of lead, which is not really within the bounds of practical politics. I don't think the STFC is going to pay me to build a detector consisting of 3 light years of lead. So what you are doing is working on the lottery principle. The chance of the ticket that you buy this week winning the lottery is extremely small. But the lottery is won most weeks because a large number of people buy tickets. In the same way, the chance of one individual neutrino interacting in your detector is minute, but you can do neutrino physics with your detector, provided that it is exposed to a very intense source of neutrinos. So a small fraction of the neutrinos will have the equivalent of winning lottery tickets and will interact in your detector. As a consequence, neutrino detectors tend to be rather large. This is the one that I work on in Japan. This is Super-Kamiokande. This is a photograph taken of Super-K during maintenance. And for scale, this is 2 Japanese technicians in a rubber dinghy. And these things that look a bit like an inside-out Dalek, these are photomultiplier tubes, which are effectively extremely sensitive light detectors. And what happens is that if a neutrino interacts in the water tank and produces a charged particle, then that charged particle may be traveling faster than the speed of light in water. Nothing can travel faster than the speed of light in a vacuum, but light in water is slowed down by the refractive index of the water. So light in water travels at about 3/4 of the speed of light in a vacuum, and the particles are not slowed down. So if the muon or electron you produce is traveling at a perfectly legal 99% of the speed of light in vacuum, it's traveling faster than the speed of light in water. And what happens is completely analogous to what happens when an aircraft exceeds the speed of sound in air. When that happens, you get a sonic boom, you get a coherent sound wave that emanates outward from the plane. In the case of a particle traveling faster than the speed of light in a transparent medium like water, you get the optical equivalent. Instead of a sonic boom, you get an optical boom. You get a coherent wave, a coherent light front that propagates outwards in a cone, symmetrically around the direction of the particle. And this is called Cherenkov radiation. And these blobs are photomultiplier tubes, which are very, very sensitive light detectors, which detect this Cherenkov radiation and can therefore tell you that a charged particle is passing through your water tank. And because you get this coherent cone of light, they can reconstruct that, and that tells you the direction of the particle, and the amount of Cherenkov radiation you detect tells you the energy of the particle. And every so often, this tank is normally completely full of extremely pure water, but every so often it's emptied for maintenance. And what these poor guys are doing is checking and cleaning each of these photomultiplier tubes to make sure that they are still in good working order and don't need replacing. And again, to give you a sense of scale, each of these blobs is 20 inches across. They're the biggest photomultiplier tubes in production. So the whole of Super-K is a cylinder, and it's 39 meters across and 41 meters tall. So it contains 50,000 tons of water. And this is, by all standards, a very large detector, but it's by no means the largest neutrino detector in existence. The largest neutrino detector in existence is this one. It's called IceCube. It is located in the ice of the Antarctic ice cap at the South Pole Research Station. It's sunk about 1,500 to 2,500 meters down in the ice. The reason for this is to reduce background from cosmic radiation, for the same reason Super-Kamiokande is located down a mine. And altogether, this detector instruments about a cubic kilometer of ice, which is where it gets its name, IceCube. And to give you a sense of scale, here's the Eiffel Tower to the same scale. IceCube is designed to detect very high energy neutrinos from astrophysical sources like active galactic nuclei. And the reason it has to be so big is that that is not an intense source of neutrinos. Such high energy neutrinos are very rare, and therefore your only chance of getting a decent data sample is to have a very, very large detector. Whereas Super-Kamiokande contents itself with measuring lower energy neutrinos, which are much more copious and therefore doesn't need to be so large. So we've had a whistle-stop tour of both supernovae and neutrinos. So let's now put this together and talk about neutrinos from supernovae. And this is a famous plot. And this shows the neutrinos that were detected from supernova 1987A. So why do supernovae emit neutrinos? Well, as I said, one reason they emit neutrinos is that they are produced when protons and electrons combine to make neutrons. That's what the initial core collapse that initiates the supernova actually does. And as we said that you can't simply make an electron disappear, that electron on the left-hand side has to be balanced by an electron neutrino on the right-hand side. And those electron neutrinos carry away as their kinetic energy the gravitational potential energy that's been released in forming the neutron star. And that produces a sharp spike of electron-type neutrinos at the instant of the formation of the neutron star. But those aren't actually the majority of the neutrinos produced. Most of the neutrinos are produced because of the high temperatures and therefore high energies available in the core of the supernova, what we call thermal production. And there are various mechanisms by which that can happen. If two nuclei scatter off each other, they can emit a Z particle, which can then decay into a neutrino-antineutrino pair. An electron-positron pair can annihilate, again via a Z boson, to produce a neutrino-antineutrino pair. An electron can be captured onto a nucleus to produce a different nucleus and an electron neutrino. This is a form of radioactive decay known as electron capture. And all of these processes can take place inside a supernova, as well as this one. And in total, even though supernovae are incredibly bright in electromagnetic radiation, calculations show that in actual fact, that visible explosion, you are only seeing 1% of the energy that's released by the supernova. 99% of the energy that's released is carried away in the kinetic energy of the neutrinos. So one reason why it would be good to detect neutrinos from supernovae is that it would allow us to verify the energetics of the supernova explosion, because when we study supernovae using their visible emission, we are only looking at 1% of the total energy release. Now, as I said, early simulations of supernovae did not explode. We have got better in the last 20 years or so, but it's still very challenging. My student, Joost Megende, before he came to do his PhD at Sheffield, he did a master's at Max Planck Garching, which is where one of the best teams of supernova simulators lives. And he used to say, he says it when he gives talks on this, that in order to simulate a supernova explosion, you need three things. The first thing you need is a three-dimensional simulation, because as we will see when I start this movie going, supernovae are not spherically symmetric explosions. The second thing you need is general relativity, because neutron stars are very compact objects, so the gravitational field near a neutron star is very strong, and the deviations from Newton's law of gravity are significant. So you can't just use GMM over R squared, you need to wheel in the general theory of relativity. And finally, because neutrinos are key to understanding supernova explosions, you need to treat neutrino interactions and the transport of neutrinos out of the core of your star accurately. So those are the three things you need. And he then says, with the current state of the art of computers, pick any one of those three. We cannot actually run simulations that that have all the bells and whistles, because it would be too computationally intensive. So the Max Planck group, as I said, is one of the world leaders at this, and they basically do 1 and 2 halves. It is a three-dimensional simulation, as you will see when I get started going. They don't do full general relativity, but they do attempt to parameterize the difference from Newtonian theory. So they don't use straight Newtonian gravity, but they don't use full-fledged general relativity either, because it takes too long to compute. And they don't have a completely accurate neutrino transport, but they have a good approximation. So this is pretty much as good as it gets. So let's see if I can get this to go. Come on. After all this build up, it better actually perform. Come on. Do your thing. It did it yesterday. It did it this morning when I tested it. Why is it not running? Come on, behave yourself. Ah. I just need to set it up now. No, it is not going to run, damn it. Nope. Nope, it really isn't going to run. Oh, what a pity. I'll see if I can set this up afterwards. In fact, I'll just come out of this and see if I can find the actual image of that thing. Let's try it again. Ah, yes, right, there we go. you can see, if you keep an eye on the scale, you will see that even though that this thing is expanding, you can now see why you need three-dimensional simulations, because it sloshes about like mad. And you get something which is in no way spherically symmetric. And if you watch the scale, you will see that this is actually expanding rapidly, and we're only simulating about the first half second of the explosion here. But at round about now, you will see that in the last tenth of a second of the simulation, it does actually increase in size enormously. So this is a simulation that does explode, and you do need, as I said, very sophisticated simulations to get the explosion to happen naturally. A lot of the simulations that are used in the field don't explode without help, so they basically have to do the computer equivalent of putting a bomb in the middle of their star to get it to explode. This is one of the minority of models that actually, where the simulation actually does lead to an explosion. So supernovae produce neutrinos. That's what our theory says, and that's what we actually observed in 1987 from Supernova 1987A. However, this is not very useful unless a supernova actually happens in our Milky Way galaxy. So how likely is that to take place? Well, the last supernova that was seen in our galaxy was by Johannes Kepler in 1604, inconveniently just before the invention of the telescope. Supernova 1987A was not in fact in our galaxy, it was in the Large Magellanic Cloud, which is a small galaxy that's a satellite of the Milky Way. So that doesn't look very good. You know, if it's been 400 years since the last supernova, what are the chances of another supernova happening in the lifetime of your experiment? Well, the first thing to say is that the one before 1604 was 1572, Tycho Brahe's supernova in Cassiopeia. So although it's been 400 years since the last one, the gap between the last one and the one before that was only 30 years. It's also true that we know that there have been supernovae since 1604 that we didn't see. For example, this supernova remnant, Cassiopeia A, is expanding, and when you compare images taken a few years apart and measure the rate of expansion and then plot it back to when it must have started, you find that this supernova remnant is about 340 years old. So it should have been seen around 1680, but it wasn't. And the probable reason that it wasn't is that core collapse supernovae tend to occur in the plane of the galaxy because that's where star formation regions are. And unfortunately, the dust that is prevalent in spiral galaxies like the Milky Way is also in the plane of the galaxy. So the chances are that the reason this object was not visible was simply that there was too much dust obscuration between the supernova and us at that time. We probably have seen it if it went off now, because we have access to the whole of the electromagnetic spectrum, not just visible light, and our telescopes are a lot better than they were in 1680. But it certainly wasn't seen in 1680. And indeed, there's an even younger supernova remnant near the galactic center that probably exploded towards the end of the 19th century, and nobody saw that one either. we can calculate the probable rate of core collapse supernovae in the galaxy by studying the abundance of an unstable isotope of aluminium, which is associated with massive stars and core collapse supernovae. And such calculations suggest that the rate of supernovae in the Milky Way at present is somewhere around 2 per century, with an error of plus or minus 50%, so 2 plus or minus 1 per century, which means that if you have an experiment that is going to run for several decades, and Super-Kamiokande started operation in 1996, so it's 25 years old, then you actually do have a decent chance of seeing a galactic supernova. And indeed, the fact that Super-Kamiokande hasn't seen one in 25 years is starting to be an interesting piece of information. It's beginning to set limits on the rate of supernovae in our galaxy. So it's not an unreasonable hope that we might see one. What could we learn if we did? Well, the first thing to point out is that the light that you see from a supernova is coming from the photosphere, just as the light from the sun is coming from the photosphere. The interior is opaque, so you can't see the light from the central core. Whereas neutrinos come direct from the interior of the explosion, and they can provide details about the explosion that you wouldn't get from the light. And so in the model that I just showed you, eventually, that slushing motion that went on at the beginning, that is called SASI, for standing accretion shock instability, and that produces rapid variations in the expected rate of neutrinos. You wouldn't be able to see that in the light because this is all taking place deep in the core of the star, but you might be able to see it in the neutrinos. We expect that some massive star core collapses indeed don't explode and do collapse into a black hole, and we have evidence of that from the LIGO signals for coalescing binary black holes. Your typical LIGO binary black hole is, the black holes are 20 solar masses or so. So this is clearly a case where the entire body of the star has collapsed into a black hole. And if that happens, you are not going to see a visible supernova, but you will still see some of the neutrino emissions. So it will, because you expect that it doesn't go direct to a black hole. You get a proton-neutron star first, and then continuing infall moves its mass above the threshold where a neutron star can't be stable, and the whole thing collapses into a black hole. So what you would get in that case would be that the neutrino emission would start and then would cut off abruptly when the black hole formed. And that might be the only evidence you get of such a massive star core collapse direct to a black hole. So if we did observe neutrinos from a galactic supernova, they would help us to improve our understanding of supernovae. We have multiple different models at the moment for the neutrino emission from a supernova, and if we could distinguish between those models, then that would lead to greater understanding of the physics of supernova explosions. We might also learn something about neutrinos. The neutrino density inside a supernova is so high that neutrino interactions with other neutrinos become important. And that is something that is incredibly difficult for a neutrino physicist to get their head around. We are used to neutrinos that don't interact with anything at all. Having neutrinos interact with other neutrinos is really not something that's within everyday experience. And this, in fact, can have impressive effects on the observed neutrino spectrum. So here are the neutrino spectra you start out with. This is the electron neutrinos. This is some other flavor. And after these neutrino-neutrino interactions, you get a coherent oscillation that above a certain threshold energy, these electron neutrinos are transformed into the other type. And this would have a dramatic effect on what you observe. And so if we were to see these coherent effects, that would allow us to learn a lot more about neutrino masses and neutrino oscillations. And these features of neutrino physics are not only of interest to neutrino physicists, they're also of interest to cosmologists, because neutrinos play a very important role in the early universe. And of course, if we were really lucky, we might get a comparatively nearby supernova. When we do simulations to understand how our detectors might perform, we tend to assume that the supernova is taking place at a distance of 10 kiloparsecs, because that's roughly the median distance of stars in our galaxy. So a circle of 10 kiloparsecs radius would include about half the stars in the potential supernovae in the galaxy. But there are stars that are much closer to us that are potential future supernovae. And the two most obvious are Betelgeuse and Antares. Both of these are red supergiants. They are both massive enough to explode as core collapse supernovae, and they have both already left the main sequence. They are because they're red and not blue, so they are at a later stage in their evolution. As I said at the beginning, those later stages go past quite quickly. So both of these stars are at the end of their lifetimes. Unfortunately, saying that these should go supernova soon is using the word soon in its astronomical sense. We could see them explode tomorrow, but they could easily last another 10 or 20,000 years. And that would be very soon by astronomical standards, but obviously not much use for us within our lifetimes. These would be truly spectacular if they did go off. Optically, Betelgeuse, when it explodes as a supernova, will be about as bright as the moon. And experiments like Super-Kamiokande would see millions of neutrinos. I mean, there would be trillions going through the detector, but we would actually detect millions of them. And the problem would not be, as it usually is with neutrino experiments, trying to tell a small signal from the background. It would be trying to prevent the huge signal from totally overwhelming your detector electronics. So this is not something that is likely to happen, but it's something that could happen. One of the problems with red supergiants is it's very hard to tell from the surface that you see what's going on in the core. So we don't really know how Betelgeuse and Antares are currently generating energy. We don't know if they're fusing helium or if they've already moved on to heavier elements. I should point out that although these are comparatively nearby stars, they're still a few hundred light years away, and they are not close enough to do us any harm. There aren't any potential supernovae within the 25 parsecs or so where the products of the explosion would actually cause significant damage to the solar system. So there is no downside to hoping Betelgeuse will explode. So to summarize, core collapse supernovae are the explosions of massive stars, around 10 times the sun's mass or higher. 99% of their energy comes out in the form of neutrinos. A galactic supernova in our lifetime would tell us a great deal about massive stars and a great deal about neutrinos, but judging by the non-observation of Cassiopeia A and the little one near the galactic center, which has a very boring name I've forgotten, it is quite possible that even despite the huge intrinsic brightness of such an object, if it's close to the galactic plane, it might not be visible to the naked eye. On the other hand, if we got lucky and Betelgeuse or Antares gave up the ghost, that would be the event of a millennium. Supernova 1006, which is the brightest historical supernova, was visible in the daytime and cast shadows at night, according to Chinese observers, but Betelgeuse or Antares would be much brighter even than that. So it's not likely that that would happen, but it's possible. Indeed, I went to a conference celebrating the 30th anniversary of Supernova 1987A, and as we were walking down from the conference venue to the restaurant where the conference dinner was going to be held, one very senior astrophysicist walking just ahead of me turned to another senior astrophysicist and said, "Whenever it's a clear night, I always look up at Orion and hope." So all we can say in the best tradition of UFO B movies is watch the skies.
Susan, thank you very much indeed for an exciting, a clear indication of the life cycle of stars. Could you, can I remind people if they could pose their questions via chat, which I've just enabled. For some reason it had been disabled. While you're doing that, I've got two questions. What's the relative mass of a neutron and a proton?
A neutron, well, a proton in the units that particle physicists use, which is mega electron volts. A proton is 938.3 and a neutron is 939.6. So they differ in mass by about by a little over 0.1%.
Right, because you produced a nice little thing showing a neutron turning a proton and electron turning into neutron and a neutrino, I think, was it?
Yes, that's right. Yeah.
And I just wondered about the mass energy implications.
Yes, indeed. As I said, this process does not go under normal circumstances because the total mass of the neutrino plus the proton is about 1.8 MeV less than the mass of a neutron plus a positron. So normally this process only goes if your neutrino has enough kinetic energy that it can make up that additional mass.
Yep.
E equals mc squared. In the case of a supernova, what provides the additional energy is essentially conversion of gravitational potential energy. That an atomic nucleus is ever so much smaller than an atom. So when there is a very strong gravitational force, it provides, if you like, a huge incentive to make things smaller.
Yep. And the second question, there was sort of tacit assumption that if you had LIGO and something like Super-Kamiokande, it would be very interesting to see some coincidence. By that I use the word slightly sort of loosely, between an event measured by the one and by the other?
That would indeed be very interesting. It is not clear that LIGO can see a supernova explosion. What makes it possible is that, as we saw with the simulation, our best models suggest that these explosions are not at all symmetrical. And it's asymmetries that cause gravity. The question is whether it would do so with a sufficient amplitude that LIGO could detect it. And I think that depends strongly on how distant the supernova is and how good LIGO's trigger systems are. But yes, certainly, there is a network called SNEWS, the Supernova Early Warning System, which is intended to alert all the relevant players, astronomers with telescopes, gravitational wave detectors, other neutrino detectors, whenever anybody sees a candidate neutrino burst that might be a supernova. And I'm sure that LIGO and Virgo are signed up to SNEWS, and that if there were such a neutrino burst, they would be searching their data for any indication of an associated gravitational wave event.
Two questions so far. From Andy Andrews, fascinating talk, thank you. You mentioned the need for decent data samples. Roughly how many hits does IceCube get per day or per week or per month?
I don't actually know. I'm not an IceCube member, or
Kamiokande for that matter.
But the key point is that for IceCube, a lot of the difficulty for them is finding their signal amongst the background, because their neutrinos are produced when cosmic rays hit the Earth's atmosphere, because cosmic rays are mostly protons, some heavier nuclei, and when they hit an air molecule in the high atmosphere, then pions are produced by such interactions, because pions are they're an up and anti-down, or down and anti-up, depending on whether they're a pi plus or a pi minus. Yeah. And they're produced in large numbers when protons interact with nuclei. And pions decay into a muon plus a neutrino. So there's a constant flux of what are called atmospheric neutrinos produced by such interactions. And it was indeed by studying atmospheric neutrinos that Super-Kamiokande established the existence of neutrino oscillations, neutrino changes of flavor, and won Kajita-san his share of the Nobel Prize. But to IceCube, to Super-K, these are signal. To IceCube, they're a bloody nuisance in the background. And so the rate that IceCube gets in terms of events in their detector is not representative of the rate that they're actually looking for, which is neutrinos from astrophysical objects. Most of it is atmospheric neutrino background.
Another question from Nigel. In the simulation, why is the expansion non-spherical?
It's because the actual collapse doesn't necessarily start in the very center of the star. And this is basically because this is a quantum mechanical process, so it's probabilistic. And therefore, the chances are, even though the center of the star is the single most likely place for it to happen, it is when you average over all possible locations, it is more likely to happen off center, and if it starts off center, then the whole thing becomes asymmetric. So it's basically caused by the fact that this is at bottom a quantum mechanical process.
Yep. I think we had a talk from Raman Prinja recently, which indicated that the signs of shells of late supernovae indicated that they weren't clearly symmetrical.
Yes, and one of the things that you notice is that, for example, if we are in the right line of sight, the neutron star can be observed as a pulsar. And you would expect the pulsar to be in the center of the shell of expanding gas that is the remains of the explosion. And for young pulsars like the crab, you see that. But for older objects, the pulsar is often off-center to the shell. And that's because the asymmetric explosion has basically given it a kick. So it's moving quite rapidly with respect to its original position. And yes, Nigel, I saw you said that the neutrino emission is asymmetric as well. Yes, indeed it is. And there are very interesting asymmetries present. Unfortunately, of course, we only get one line of sight. It would be terrifically useful if we had a network of observers over the entire galaxy who could look at the supernova from different angles. But sadly, until we discover faster than light travel, that's not going to be a practical proposition.
Another question, what is the speed of a neutrino?
It's very, very close. Typically, it's very, very close to the speed of light. Because they are so low in mass, essentially any object which is exactly massless will travel at precisely the speed of light.
Yep.
Neutrinos are not massless, but they have very, very small masses. So, for example, the current upper limit on the neutrino mass is 1 electron volt. The energies of typical supernova neutrinos are around 20 million electron volts. So the kinetic energy is 20 million times the mass. So this is, in the jargon, ultra-relativistic, and it is a very, very good approximation to assume that the neutrino is traveling at the speed of light. The only exception to that is that we expect there to be a cosmic neutrino background, analogous to the cosmic microwave background, but at an even lower temperature because it gets released earlier and has a higher redshift. So it's at about a temperature of 1.9 Kelvin as opposed to 2.7 Kelvin of the cosmic microwave background. And if you take that, the energy implied by that temperature, and you take the mass limits that are implied by the observations of experiments like T to K, you find that at least one species of cosmic neutrino background neutrino is actually non-relativistic. And this is nearly as difficult an idea to get your head around as neutrino-neutrino interactions. We are so used to assuming that all neutrinos travel at the speed of light. I did this calculation when I was teaching the cosmology course, and I was really quite shocked to find that there exist a lot of neutrinos, and the cosmic neutrino background is about 400 neutrinos per cubic centimeter, and about something like 130 of those are actually non-relativistic, and that's incredibly difficult to imagine. The trouble with this is that nobody has ever come up with a plausible scenario for detecting the cosmic neutrino background. And the reason for this is that the probability that a neutrino will interact is roughly proportional to its energy. So ice cubes, very high energy neutrinos, a much larger fraction of them interact in ice cube than our lower energy neutrinos interacting super-K, but these incredibly low energy neutrinos to first, second and third approximation don't interact at all. Nobody's ever managed to think of a detector concept that would stand any realistic chance of detecting them.
Any other questions? Susan, thank you very much indeed. I've found that fascinating. I believe others have as well. Thank you indeed for your time and your effort and the excitement of your presentation.
Well, thank you. Thank you for the invitation. And as I said to you at the start, I'm really sorry that my original date didn't happen because my internet crashed on me. So I'm glad that this time we managed to make it through with no interruptions.
Good moments are always worth waiting for. Thank you, Susan.
Thank you very much.
Just to note, you should have had an email, if not somewhere in your in-tray or possibly in your junk mail. There's a note to say our next meeting is not on the first Thursday of July, but on the second Thursday of July. It will be our AGM, and your note will point out we haven't had an AGM. We didn't have one last year because we had no mechanism for doing so. This one will be an interesting experiment of Zoom. I'm hoping that Rob will start off with a July and August what's up from Rob, but I would encourage you all to participate. This is your society. Would love to hear your ideas, your comments, brickbats as appropriate, and it's an opportunity to be involved in choosing the committee for our next session. Meanwhile, keep safe and all the very best.